For the third part of the trigonometric identities, we'll be discussing double angle identities. For the double angle identities, let's have sine. For sine of 2a, that's basically 2 sine of a cosine of a. For cosine of 2a, you'll have cosine squared a minus sine squared a. However, when we apply the Pythagorean identities, removing sine, that's actually equivalent to 1 minus cosine squared. That's why you'll have the 2 cosine squared a minus 1. However, when I remove the cosine squared a and replace that with 1 minus sine squared a, it becomes 1 minus 2 sine squared a. Whereas for tangent, it's basically 2 tangent of a all over 1 minus tan squared a. Do take note of the quadrants. We're in the first quadrant, all trig functions are positive. In the second quadrant, sine and cosecant are positive. Third, tangent and cotangent are positive. And lastly, for cosine and secant, it's the fourth quadrant where they are positive. So let's try. It says here that tangent theta is 7 over 24, and then the theta is in quadrant number 3, so maybe it would be helpful if we draw the angle in the third quadrant. So if this is theta and then tangent is opposite over adjacent, that means this has to be negative, this has to be negative. And then when you get the hypotenuse, let's just apply the Pythagorean theorem. This would give us a special triangle, 7, 24, 25. So let's determine the exact values of sine 2 theta, cosine 2 theta, and tangent 2 theta. By the way, some of you might be asking how the formulas were derived. For example, if I say sine of 2 theta, this is basically sine of theta plus theta, or sine cos plus cos sine. That's why you have 2 sine theta cos theta, and it follows for the cosine and for the tangent. So let's apply the formula in here. It's basically 2 sine of theta, it's opposite over hypotenuse, and cosine theta is adjacent, negative 24 over hypotenuse 25. So 7 times 24 times 2 is basically 336 all over, this is 625. So basically, that's the answer for sine of 2 theta. Let's try the cosine of 2 theta. Let's follow the formula. Cosine of 2 theta is cosine squared theta minus sine squared theta, which is actually the first one. So I can say here, cosine squared of theta, adjacent over hypotenuse, you have there 24 over 25, negative, square that, and then sine is 7 over 25, that's negative, and then square that. This is gonna be 24 squared is 576 over 625. 7 squared is 49 over 625. 527 over 625. So this is your answer for cosine of 2 theta. And then lastly, we have the tangent 2 theta. You'll have 2 tan theta all over 1 minus tan squared of theta. So for 2 tan theta, that's 2 times tangent is 7 over 24, positive, all over 1 minus 7 over 24 squared. So this is 7 over 12. This is 1 minus 49 over 576 is 527 over 576. So 712 over 527 over 576. You'll have 336 over 527. So let's go to another one. Here, you're asked to rewrite sine to the 4 of 2x in terms of cosine only. Let's try this. I can say that this is basically sine of 2x quantity to the 4th power. And then sine 2x is 2 sine of x cosine of x. So when I apply the power, this gives me 16 sine to the 4x cosine to the 4x. So I don't have any problem with the cosine to the 4x, but I have a problem with my sine to the 4x because this is still sine. So what I would do here is, maybe I can say sine squared x squared, and then this is cosine to the 4 of x. Take note that sine squared x, that can be replaced by the Pythagorean identity. So I can say this is 1 minus cosine squared of x, and then that's raised to the second power. So if I expand this, this gives me 1 minus 2 cosine squared x plus cosine to the 4 of x, and then there's cosine to the 4 of x. So I'll have 16 cosine to the 4 of x. 16 times 2 is 32 cosine to the 6 of x plus 16 cosine to the 8 of x. So this is how we expand this and rewrite it in terms of cosine only. Let's try another one. Cosine of 2a. So for cosine, as I said, we can choose the left side or the right side. I'll show you two solutions. For if I would like to manipulate the left side, cosine of 2a, that's cos squared a minus sine squared a. And then take note that cosine, I can rewrite that as 1 over secant squared a minus this one, let's just keep it as sine squared a. So if I would combine this, let's just write an over 1 here, imaginary over 1. So I would have in the denominator secant squared a, which is what I would like to prove. I have it there. 1 minus sine squared a times secant squared a. But the thing is, I don't have sine or secant on top. I have a tangent. Do take note that sine squared a times secant squared a can be written as sine squared a times 1 over cosine squared a, which is sine over cosine. This one is actually tangent squared a all over secant squared a. So this one and that one would be the same. So we were able to prove the identity. Now what if I manipulated the right side? So here you manipulated the left side. Here, what if what you manipulated was the right side? Let's try. I can separate that as 1 over secant squared a minus tangent squared a over secant squared a. 1 over secant, that's cosine squared a, minus tangent, I can say that this is sine squared a all over cosine squared a times secant squared a. When you move it up, that's actually cosine squared a. And then you'd be able to cancel this out. So you'll have overall, you'll have here cosine squared a minus sine squared a. This one is cosine to a. So now we were able to prove using the right side, it's equal to the left. If I'm to prove this, if I would like to start with the left side, let's just say cosecant 1 over sine 2a is cosecant, and then cotangent is cosine 2a over sine 2a. If I combine them, I would say that is 1 minus cosine 2a all over sine 2a. So what's the next step? Cosine 2a is cosine squared A minus sine squared A. Don't forget the parenthesis. And then the bottom, I can say that that's 2 sine of A cosine of A. And then let's just distribute 1 minus cosine squared A plus sine squared A all over 2 sine of A cosine of A. Again, some of you might ask, why did I have to change the sine to A into simply A? Because the right side that I would like to prove only contains tangent of A, not tangent of 2A. So if you notice in here, this term 1 minus cosine squared A is actually sine squared A. That is Pythagorean identity. So if I were to simplify this, that becomes 2 sine squared A all over 2 sine of A cosine of A. If you want to cancel out terms, the 2 cancels out, the square, so one of the sine A's cancel out, and then the sine A. You'll be left with sine A over cosine of A, which is tangent of A. And then you have proven the identity. Let's just place equal signs here. Now in here, if cosecant of A is equal to 2, tangent of A is less than 0. So when is cosecant greater than 0? That is in the first and the second quadrant. Tangent of A is less than 0 in the second and the fourth quadrants. So since the second quadrant repeated, that means angle A can be found in the second quadrant. So let's draw angle A in the second quadrant. This is your A. It says there cosecant. Cosecant is hypotenuse over opposite. So that means using Pythagorean theorem, this is square root of 3, but then it goes to the left, so that is negative. Now you're being asked, where is 2A located? The thing is, you can't just say that, for example, in the second quadrant, an angle can be 91 degrees. 91 times 2 is just over 180, so that's 182. So it would lie in the third quadrant. However, if the angle, for example, is 170, that would give us 340. It would be in the fourth quadrant. So we're not sure in which quadrant 2A would lie. So how do we do that analytically? I can say that if I would like to solve for sine 2A, what would be the symbol for sine 2A? 2 sine A cosine A, that would be 2. Sine theta is opposite of our hypotenuse. Cosine theta is square root of 3 over 2, but that's negative. So that means the answer is negative square root of 3 over 2. And then let's try solving for the value of cosine 2A. You know that cosine 2A would have a formula, cosine squared A minus sine squared of A. Cosine squared would be square root of 3 over 2 negative, but then you square that, minus sine squared is 1/2 squared. So this is 3/4 minus 1/4. So all in all, you'll have 2/4 or simply 1/2. So the thing is, sine 2A is negative, but cosine of 2A is positive. So this one would be negative in the third and fourth quadrants, whereas cosine would be positive in the first and fourth quadrant. So since fourth quadrant repeated, that means angle 2A is in quadrant number 4. Can you follow? Because actually this one, what angle is this? This is 150. 150 times 2 at actually 300. It's already above 270 degrees, more than 270 degrees, which is correct. Lastly, let's try this. So for this one, maybe what I can do is my sine of 3a can be rewritten as sine of 2a plus a. So I have sin cos plus cos sin. So you notice that sine has to be purely sine of a. I can't have any 2a in here. So that means this one has to be 2 sine a cosine a times another cosine a, which is the one on top, plus the cosine has to be purely sine. So I cannot have cosine squared minus sine squared. Take note, for cosine there are actually three formulas: cosine squared a minus sine squared a, but what I need is purely sine. So 1 minus 2 sine squared a is for the cosine. So that means this one is 1 minus 2 sine squared a. This one is sine a from the top. So I'll have 2 sine a cosine squared a, and then plus, in here I have purely sine a minus 2 sine cube of a. So we're getting near there. It's purely sine, purely sine. The problem is there is cosine. So that cosine, I could still replace that using the Pythagorean identity. And then let's just copy the others. 2 sine cube of a. This one, if I distribute this is 2 sine of a minus 2 sine cube of a plus sine of a minus 2 sine cube of a. So now we can combine those similar terms. This one can be 3 sine of a minus 4 sine cube of a. So we were able to actually prove what is needed to be proven. The problem is you really have to always recheck what you're trying to prove. Like if I want my left side to be the same as my right side, I would try to target all those. Like I need to get rid of the 3a, make it purely letter a. And then since I don't have any cosine in here, all the cosines, maybe we can change them to sines eventually. Alright? I hope you understand these. Thank you very much. Good luck.